Okay, these are just a few notes on the trapezoidal rule and Simpson's rule. And these things are pretty well explained in the book, so I think if you read these and look at the examples, you'll be all right. But basically, we've used the midpoint, the right rectangular, and the rectangle approximation, the left rectangle approximation, or the RRAM and the LRAM and the MRAM, the midpoint. Now this is trapezoids, and if we use trapezoids, you see they're going to conform to the curve even better. So trapezoids, to do this, approximating the area under the curve, is a pretty good approximation. So this is we can simplify that rather than drawing all these individual trapezoids and working this out. If we use subintervals of uniform length, then we can use this, what we call a trapezoidal rule, and it makes it a lot easier to calculate this. So here's basically the gist of it. Let's say we have an interval, we're going from A to B. We want to find the area under the curve of this function. We want to approximate it by using trapezoids. Then if we use these subintervals that are all the same length, that would be the total length b minus a divided by the number of subintervals we're using, n. That would be h, if that's h. Then this is going to work out as the height of each of these trapezoids. In other words, if this whole distance is b minus a, and I have n of these little trapezoids, then each will have a height, if we look at it this way, because these are the two parallel sides, which are what we call the bases, and these are the heights of these trapezoids. Now the actual lengths of these parallel sides will be given by actually the value of the function at these different points. So y sub 0 would actually be this length here, y sub 1 would be this length here, that's f of x sub 1, f of x sub 0, f of x sub 2, etc. would give me y sub 2. So that's what actually I would be using for my bases of my trapezoids. So for this very first trapezoid as an example, the height is h, and then base 1 plus base 2 would be y0 plus y1 over 2. For the second trapezoid, the height would be h again, and then I would have y1 plus y2, etc., etc., etc. We keep adding them up till we got to the end. The last ones would be, base would be h, and I'd have y sub n minus 1, a y sub n, divided by 2, and that would give me the two bases. That would give me the area of that trapezoid. So basically, that's the gist. Now, what we can do is we can factor out the h's, because they're all the same. We can factor out the 2's, and what's left is y sub 0, y sub 1, and then another y sub 1, y sub 2. Then there'll be another y sub 2, y sub 3, etc. And what happens is we notice we just have one of the endpoints, y sub 0 and y sub n, but because we've got these other endpoints that are occurring in two trapezoids, we end up with actually 2 y sub 1, 2 y sub 2 all the way out. And this is basically the gist of the trapezoidal rule. Where y sub 0 is f of x sub 0, then the x sub 0 is actually a, the left endpoint. Y sub 1 is f of x sub 1, and all the way to y sub n, which is f of x sub n, which is actually b. And they actually formally outline the trapezoidal rule over on page 307. So in your book, if you take a look at it, it's right there. And they give you all the parameters. Again, they restate the parameters. So this is basically what we have here. Okay, so that's what we're talking about. Okay, so that's the trapezoidal rule. I did an example. They've got an example in the book. Again, this is on page 307. This is a slightly different example I picked. So let's take a look at this. And use the example, use the trapezoidal rule, and I kind of try to make it easy, but it didn't come out that easy. N equals 4 to estimate this integral from 1 to 5 of 1 over x dx. So b minus a, 5 minus 1, that would be b minus a. And my number of intervals was 4, so my h was just 1. So it was just h over 2, and then this was basically the statement of the trapezoidal rule. So that's what you want to do, stated like this. Y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus 1y sub 4. And those would be your five little points. This is your left endpoint, your right endpoint, and these are your subdivision points. So you see you do have 1, 2, 3, 4 trapezoids. You just happen to have 5 of these y values corresponding to the 5 x values that you would have. And then you just put this in. So this is going to be 1 over 1. So this works out because my points are just going to be 1, 2, 3, 4, 5, my x points. So I try to make it easy. So it would be 1 over 1 plus 2 times 1 over 2 plus 2 times 1 over 3 plus 2 times 1 over 4 plus just 1 times 1 over 5. I thought that was going to work out easy. It didn't work out all that real easy. Anyway, this is just going to be 1 plus 1 plus 2/3 plus 1/2 plus 1/5. Okay? Again, this was 1 over x, and my x subintervals were 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Those are my x sub zeros. X sub 0 was 1, x sub 1 was 2, x sub 2 was 3, x sub 3 was 4, and x sub 4 was 5. So it worked out pretty much like that. It was just 1 over that. And then times these numbers here, 1, 2, 2, 2, 1. And then again, I simplify that, 1/2, 1/2, 2/3, 1/2, 1/5. And then this had a common denominator 30, so I made this 2, 1 plus 1 is 2. And you have to do some arithmetic, 30 plus 15 plus 60, well that's another 30, so that was 3 and 11 over 30. Then I made an improper fraction, 101 over 30 times 1/2 became 101 over 60. Then I divided the top by the bottom, I get 1.68. And then I worked my calculator out just to see what I would get. And you see basically what I did was this was the 101 over 60, and I got 1.68. That's how I got this over here. And then I used the integral. I used the math 9, 1 over x, and I integrate from 1 to 5, and I got 1.61 approximately. So my approximation was a little bit off, but not too bad. So that's the trapezoidal rule. Okay.